So hi everyone, we'll start after a couple of minutes. Huh? So hi everyone, am I audible? Can someone confirm? Hello. Oh, actually I don't follow cricket, but okay, let's concentrate on our lecture. I think later we can discuss cricket. By the way, am I audible? Can someone confirm? Okay, thank you. So good afternoon everyone. My name is Musab Rafiq. So today we'll be discussing week 7 related problems for the course Digital Electronic Circuits. So let me just share the screen and we can have our routine intro and all. Okay, just a second. Okay, let's just start with our normal intro. Actually, we are bound to do this intro every time. So good afternoon everyone. My name is Musab Rafiq. I'm your course TA for the course Digital Electronic Circuits. Today we'll be discussing problems related to week 7 tutorial, and this course is taught by, as you know, Professor Gautam Saha from IIT Kharagpur. I am from IIT Kanpur. I am a PhD student in the Department of Electrical Engineering. So today is 19th March and this is a week 7 tutorial. So week 7 will have problems related to mostly to flip-flops, and I have highlighted the week 7 contents. And also whenever I solve a particular problem, I will be giving you a couple of minutes after that. You can ask me your doubts, and also new participants will only be admitted after I solve a problem. In between I won't be able to admit as I don't have access to the Google Meet that time, and so you can wait that time, but once I have admitted you, you can join anytime. So someone is in the waiting room. Let me just admit that person first, and after that we can start with the question number 1. So actually no one is here. Okay. So let me just start with the question number 1. So question number 1 of today's live problem session is convert a T flip-flop to D flip-flop. So I have started with this question, and you might have seen that these types of questions are occurring these type of questions occur many times, and I'll just show you how we approach to these problems. And in today's problem session I have kept 2-3 problems based on these conversions. So these are quite important from examination point of view and also from concept point of view. So you should be able to do these type of problems. So that's why I have kept this thing, and I'll just show you the general way of doing these problems. So there are 5 essential steps that you need to follow whenever you do these type of problems, that is the conversion of one flip-flop to another. So these 5 steps are, you need to remember these 5 steps. This will help you. So it's just how I approach these problems. You may have another ways, but usually it's these way only. So what is the first way? The first way is we have to identify the available and required flip-flop. So whenever we are given a problem, we have to look for the available and the required flip-flop. Then we have to make the characteristics table of the required flip-flop, and followed by the excitation table of the available flip-flop. And finally we have to jot down the expression of available flip-flop, and at the end we can have a circuit. So what are the steps? First we need to find out the available and required flip-flop. So here we need to convert T flip-flop to D flip-flop, right? So what is our available flip-flop? Our available is T flip-flop and D is our required. So let's just write it down. So T flip-flop, so I'll just write TFF in short for T flip-flop and DFF in short for D flip-flop, right? So T flip-flop is our available flip-flop and D flip-flop is our required flip-flop, right? So we are done with the first step. This might seem a pretty straightforward step, but sometimes people get confused with this step. So write down this carefully. So we have this available flip-flop and D flip-flop is our required flip-flop. Then we have to make characteristics table of the required flip-flop. So we need to make characteristics table of the required flip-flop. So characteristics table, what does the characteristics table have? It has present state and present input as input and next state as the output. So we have Qn and then we have the D. So Qn will represent our present state and D will represent my present input. So let me just write down the contents of the table, characteristics table: 0 0 0 1 1 0 and 1 1. So now we need to write down the next state. So next state will be represented by Qn plus 1, right? So for D flip-flop we know that the output is dependent on input, so Qn will be n plus 1 is simply equal to D. So D is equal to 0, it will just follow the input 0 1 0 1, right? So we are done with the first step and we are done with the second step. First step was to find the available and required flip-flops. Second step was to make the characteristic table of the required flip-flop. Now we have the third step, to make the excitation table of available flip-flop. So excitation table is made from the present state and the next state inputs, present state and the next state, and we have the input here. So what is the input for excitation table of T flip-flop? So it's T, and based on Qn and Qn plus 1 we need to find out the value of T here. So we know that it follows the XOR logic. So we know Qn and Qn plus 1, it will have 0, it will have 1, it will have 0, it will have 1 and it will have 0. You can find this out from this thing here. So in case you don't remember, so I have T, I have Qn, and then I have Qn plus 1. So my here is 0 0 0 1 1 0 1 1. So when T is equal to 1, the output toggles. So here it will go with 0 1. So input was 0, it will toggle to 1, and our input present state was 0, it will toggle to 1, and present state was 1, it will toggle to 0. So and then using this I have constructed this, right? So now I have to write, so I've done with my third step. Now I have to write my fourth step. So what is the fourth step? So I have to write the Boolean expression of available flip-flop. So I have to write the Boolean expression of T flip-flop in terms of the D and Qn, right? So T will be equal to, if you carefully look at this, D and Qn, it is simply equal to, T is equal to D XOR with Qn, right? Look at this column and look at this column. So this is T is equal to D XOR Qn. So we have our fourth step, and finally we need to draw the circuit. So what was our available flip-flop? Our available flip-flop was T flip-flop. So this was a T, and here will be my clock, and here is Qn. So T, it will go like this, and it will go like this, and one will be D. So this is my D flip-flop using the T flip-flop. So these are some of the general steps you can follow, and based on these steps we'll solve the problems that will be next problem we'll solve using these steps only. So any doubts in here? Okay, today actually the number of participants are more, so I think chat box will be feasible to use this time. So if you're not able to type in your doubts using chat box, then only you can use your mics. Otherwise you can use your mics, no issues. So I think we can move forward to question number 2. So question number 2, let me just check the question number 2. So question number 2 asks us, implement D and T flip-flop using JK flip-flop. So it's another conversion problem based question, and this time it's an MCQ question. So we have to find the conversion of D and T flip-flop using JK flip-flop. So again, let's just remember the 5 points. So what was the point 1? Point 1 was to find the required and available flip-flop. So the available flip-flop here is JK, initials of my home state, and after available we have to find the required. So required are D and T. So here we are we have to do 2 conversion problems for D and T using JK, right? So point 1 is done. Number 2 point is write the characteristic table of the required flip-flop, right? So if you just check, write the characteristic table of required flip-flop. So here I'll just divide this thing, because towards the right hand side I will just do this thing, D flip-flop, and towards the left hand side I'll just do T flip-flop. So let's just write down the characteristics table of the required flip-flop. So we have Qn and T. So here we are implementing T this side, and here I am using D. Qn and T. So we have 0 0 0 1 1 0 and 1 1, and Qn plus 1 is equal to, so whenever the T is 1, my next state will be toggle. So here it's 0, it will remain at 0, it will 0, it will remain at 1. So at 1 it will toggle, and at 1 it will toggle. So this is my characteristics table. Now I will write down the characteristics table of D flip-flop. So here the required is D, here the required was T, right? So Qn, T, and my next will be Qn plus 1. So it is 0 0 0 1 1 0 1 1. It will just follow the D, 0 1 0, it will just follow the input, right? Now I have to make the excitation table of the available flip-flop. The available flip-flop is JK. So this is the point number 3, and I have to make the excitation table of JK flip-flop. So excitation table, if you remember, let me just write down this first, the characteristic table of JK somewhere. Let me just introduce a slide first. So here first I will write the characteristics table of JK, then I will construct excitation table from that. my present inputs, my present states, and finally the next state. 0 0 0. Sorry, this is 1 1 0 1, right? And here I have 0 0 1 1 0 0 1 1 and 0 0 0 1 1 1 1. So my inputs both are 0 0, so output will be equal to Qn, so it will be 0 1. My inputs are 0 1, so output will be 0 0. My inputs are 1 0, so it will be 1 1, and my inputs are 1 1, so it will toggle, so it will be 1 0, right? Let me just check it. So 0 1 0 0 1 1 0, right? Now I have to construct the excitation table out of it. So Qn, and this is Qn plus 1. So here I will have 0 0 0 1 1 0 1 1, and here I will have J, and here I will have K. Qn and Qn plus 1 is equal to 0 0. So 0 0, this is this, and 0 0, it's this. So J remains as 0 and K is varying, so K will be don't here. Now 0 1 0 1 is this and this. J is 1 and K is varying, so 1 don't care. Similarly for this is x1 and this is x0. So this is my excitation table for a JK flip-flop. Now here what we have Qn and Qn plus 1 is 0 0. So 0 0 we will have 0 comma don't care. Then we have 0 1, for that we will have 1x. Then we have 1 1. So take here it's not 1 0, here we have 1 1. So 1 1 means x0, and finally we have 1 0, that means x1, right? So this is the excitation table of the available flip-flop. Now we will draw the excitation table of available flip-flop here. So we have 0 0, that means 0x. Then we have 0 1, that means 1x. Then we have 1 0, that means x1. So 1 0 is x1. Then we have 1 1, so x0, right? So we are done with our 3 steps. Now we have to write the Boolean expression. So first we'll write the Boolean expression for J. So J is equal to, for, and we'll just use K-map. Here I have Qn, and here I have T 0 1 0 1. So this thing is like this, 0 x 1 x, and we'll have this pair, so that implies J is equal to T, right? Now we'll have for K, similarly for K also we'll have, this is Qn and this is T. So this is 0 0 is x, 0 1 is x, 1 0 is 1 0 is 0, and 1 1 is 1. So again K is equal to T, right? Now we'll do for D flip-flop case. So D is equal to, sorry, J is equal to, here I have Qn, here I have D. 0 0 it's 0, 0 1 is 1, 1 0 is this and this, right? So J is equal to D. Now for K we have zero zero is cross, 0 1 is cross, 1 0 is 1, and 1 0 is 0, and for that we have this K is equal to D complement. So my 4 conditions are, for T flip-flop J is equal to T, K is equal to T. So J is equal to T, K is equal to T is this one and this one. And for D flip-flop is J is equal to D and J is equal to T. Let me just write here. J is equal to D and K is equal to D complement. J is equal to D and K is equal to D complement. So the answer is option B. So option B was the correct answer to this question. Any doubts? Okay, I guess some of you have done it. So let me just check, am I missing anything? No. Now we can move forward to question number 3. Should I proceed with question number 3? Okay, I guess there are no doubts. Yeah, question. Any doubt, Kailash? Okay, I think then we can proceed to question number 3. So, question number 3 asks us, the above synchronous sequential circuit built using JK flip-flop is initialized with Q2, Q1 and Q0 equal to 0, 0, 0. The state sequence for this circuit for the next 3 clock cycle is, so we need to find out the states for the next 3 clock cycles given the initial state was 0, 0, 0. So how will we do it? First we write down the present states here, Q2, Q1 and Q0, and this is, and here we will write down the inputs. So this is 2, this is 1 and this is 0, just for the labeling purpose. So J2, so J2 is equal to, what is J2 equal to? It's equal to Q naught bar, right? It's equal to Q naught complement. J2 is equal to J2, oh no, sorry, J2 is equal to Q1 complement, sorry. See, this J2 is equal to Q1 complement, and K2 is equal to Q0, right? And J1 is equal to Q2 simply, and K1 is equal to Q2 complement. Finally we have J0 is equal to Q1 and JK0 is equal to Q0 complement, right? And then we have the next states, so that is Q2 plus, Q1 plus and Q0 plus, right? So initially our states are 0, 0, 0. So my J2, which is Q1 complement, so it will be 1, K2 is 0, K2 is equal to Q0 is equal to 0. So my J2 and K2 are 1, 0. So when I have input J and K as 1, 0, my next state will be 1. Then J1 is equal to Q2, so Q2 was 0, so it will be 0, and K1 was Q2, so K2 complement will be 1. So 0, 1 means 0, so I'll write 0 here. Then J0 is equal to Q1, so it's 0, and K0 is equal to Q0 complement, so it will be 1, so again 0. So this is my next state. This will be the present state for the next state inputs. Now J2 is equal to Q1 complement. Again Q1 is 0, so it will be 1, and Q0 is equal to 0, so it will be 0. So 1, 0, it will again be equal to 1. Then J1 is equal to Q2, which was 1 here, check here, and then K1 is equal to Q2 complement, which will be equal to 0, so it will be 1. J1 K1 is equal to 1, 0. Then we have J0 equal to Q1, which is equal to 0 here, and Q0 is equal to Q2 complement, which will be 1, so it will be 0. So my next state is 1, 1, 0, which will be the present state for the third cycle, so it will be 1, 1, 0. So Q1 complement, it will be 0, and Q0 will be 0, right? Then we have J1 equal to Q2, which will be 1, and Q2 complement will be 0. For 0, 0, it will remain as, for when J equal to K equal to 0, my output next state will be equal to present state, so it will be 1. And for 1, 0, it will be 1, and for J0 equal to Q1, it will be 1, and Q0 complement will be 0, it will again be equal to 1. So the next 3 states are after 0 0. So it's 1 0 0, 1 1 0 and 1 1 1. So it is 1 0 0, 1 1 0 and 1 1 1. 1 0 0, 1 1 0, 1 1 1. So option C is my correct answer. So any doubts here? Okay, no doubts. So let's just proceed to this was question number 3. Okay, so this was question number 3. Let's just proceed to question number 4. So the question number 4 asks us how to implement a clocked SR latch using only NOR gates. So using only NOR gates. So the available gates that we have is NOR gates, and we have to implement the clocked SR logic. So what is this clocked SR logic? So we have to implement this circuit using only NOR gates. So let's just write the output equation of this clocked SR gate. So Q of n plus 1 is equal to, so Q of n plus 1 is equal to, so what is the input here? So it's R and with C, so it's RC, then it's NOR with Q complement, so it's NOR with Q complement. So this is my output, right? And Q n plus 1 complement is equal to, so it's SC NOR with Q. So let me just write Qn and this Qn. So now we have to implement this boolean expression simply using NOR gates only. So we can write using NOR gates. We have to break it in OR gate first. So RC. So RC can be written in NOR gate as R complement plus C complement then whole complement. So we know that A complement plus B complement whole complement is equal to A complement B complement whole complement, which is equal to AB. So we are using the De Morgan's law here. So RC will be equal to R complement plus C complement, then Qn complement as it is, and then we have this whole complement. So this here is a NOR gate, then this here is a NOR gate. So this is my expression using NOR gates only. Now for Qn plus 1 complement, I'll again use this logic, S complement plus C complement whole complement plus Qn and then the whole complement. So this is my, so this is one NOR gate and this will be going to another NOR gate. So Qn plus 1 is equal to R complement plus C complement whole complement plus Qn complement. So this is R complement plus C complement whole complement plus Qn complement whole complement. So this is option B, and the Qn plus 1 complement is equal to S complement C complement whole complement plus Qn whole complement. So option B is my correct answer. So any doubts here? Any doubts in this question or the questions that we have solved previously? Okay, okay, so you will have an idea how to approach it. Okay, that's right. Any other doubts regarding any of the questions we solved earlier, or should we proceed? Okay, let's move forward to, this was question number 4. Now let me just check question number 5. So the question number 5 asks us how many flip-flop circuits are needed to divide by 16. So we need to find out the number of flip-flop circuits required to divide by 16. So whenever we do this divide by 16, it means we have to find the modulus. So divide by 16 means mod 16. And mod 16, so in general we have this mod n, and for this the criteria is n should be less or equal to 2 raised to power n, where n is the number of flip-flops. So here 16 should be less or equal to 2 to power n, and the smallest number the smallest n that I can think of that will satisfy this condition is n equal to 4. So the minimum number of flip-flop circuits required to implement this divide by 16 logic is n equal to 4. So actually I just want to say one thing here. Actually you will be discussing these things in I think week 9 lectures. I wasn't aware of that counter will be discussed in week 9, so but I kept this problem still here. Otherwise there were few counter problems also, but I changed them with flip-flops only. So counters you will be discussing in week 9. So with regarding to this you will be discussing more in week 9, and that time we can discuss in thorough detail, but it's just a simple question. There was no complexity here, so that's why I kept it here only. So any doubts? Okay, so let's just move to question number 6. So question number 6 asks us, so actually I have marked it in yellow, so that means I'll just ask you guys to do it first, then I'll just show you the solution. So I'll just read out this question for you, then we can I'll just wait for you guys, then I'll just show the solution. It's 3:33. I think it will take around 6 to 7 minutes, so let's just say it will take around 7 minutes, and at 3:40 you guys can type in your answers, then I will show the solution. So the truth table of XY flip-flop. So we have a XY flip-flop is shown below. Design the flip-flop using JK flip-flop. So we have these 4 options, and among these 4 options, one is the correct option. So the crux of the question is, so you have to implement an XY flip-flop using a JK flip-flop. The truth table reads as follows: XY Qn plus 1, 0 0 Qn bar, 0 1 1, 1 0 0, 1 1 Qn bar. So you have to implement using JK flip-flop. So I'll just wait for 5-6 minutes, then I can show you the solution. Was question clear to you guys, or should I repeat? Okay, I'll do it. So have you guys done it? Okay, it's 3:40. Let me just show you the solution. So it's another conversion problem. So let me just check my mic is on. Yeah, it's another conversion problem, and the 5 steps that I told you to remember. So let's just proceed with that only. So the first one was to identify the available and the required flip-flop. So available was JK and my required was XY. We don't know what XY is, but we have the truth table, so no issues. Then we have to write down the characteristic table of the required flip-flop. So the required flip-flop is XY. My inputs are X and Y, and my current state is Qn, and my final state will be Qn plus 1. So it's 0 0 0 1 0 1 0 1 0 1. Here I have 0 0 1 1 0 0 1 1, and finally 0 0 0 1 1 1 1. So let's just fill this characteristic table based on the truth table. So my X and Y are 0 0. My X and Y are 0 0. My Qn plus 1 will be Qn complement. So 0 0 means 1 0 here, simply Qn complement. And for 0 1 it's 1 1 1 1, and for 1 0 it's 0 0 0 0, and finally for 1 1 it's again Qn complement, so it will be 1 0, right? Now I have to write down the excitation table of the available flip-flop. So my available flip-flop is JK flip-flop, so it's J and K, and excitation table of JK, if you guys remember, we did earlier. So it's 0 0 0 1 1 0 1 1, and if we just correct them, it's Q and Qn plus 1. My J and K will be then equal to, it should be 0 don't care, 1 don't care, don't care 1, don't care 0, right? So Qn is 0 1, so 0 1 it will be 1 and don't care. Then it's 1 0, it will be don't care 1. Then it's 0 1, 0 1 will be 1 and don't care. Then it's 1 and 1, so don't care 0. Then it's 0 0, then it's 0 don't care. Then it's 1 0, then it's don't care 1. Then it's 0 1, it's 1 and don't care. Then it's 1 0, it will be don't care 1. So let me just check whether I have written it correctly. 1 don't care 1, don't care 0, don't care 1, don't care, don't care 1, don't care 0, don't care 1, don't care 1, right? Now let's just write the equation. So here J, so it will be equal to, let me just draw the K map here. I can draw it here for J. So it will be X Y Qn 0 1 0 0 0 1 1 1 1 0. So let me just fill it. It will be 1 X 0 X X 1. So we can have it like this and like this. So J will be equal to, from this it will be X complement, and from this it will be Y, X complement plus Y. So J is equal to X complement plus Y. Now it's the turn of K. So here I'll write X Y Qn. So 0 1 0 0 0 1 1 1 1 0. So it will be X 1 0 X x1 x0 x1 x0, and it's x1 x1. So it will be this and this. So k will be equal to, from this I will get y complement, and from this I'll get x. So my j is equal to x complement plus y, so it's x complement plus y, and my k is equal to x plus y complement. So my correct answer is option D. This is my j and this is my k. So option D is our correct answer. So were you guys able to do it? Any difficulties? So option D is my correct option. So now let's move forward to the next question, that is question number 7 of today's live session. So the question number 7 asks us, for j is equal to k is equal to 1 in a jk flip-flop will be considered as. So we have to find the, let me just wait a second. J is equal to 1 is equal to j is equal to k is equal to 1 condition. We need to find out what that condition is called as. So let me just draw the truth table of JK flip-flop. You guys must be knowing it, but let me just show the complete solution. 0 0 1 0 1 1, and my qn plus 1 will be equal to q 0 1 and qn complement. So we need to find what this condition is called. So what this condition is called, so 1 j is equal to k is equal to 1, qn plus 1 is equal to qn complement. So the output toggles. So that means this is the toggle condition. This was a straightforward question. I don't think there will be any doubts in here. So now let me just move forward to question number, let me just check what is this, question number 8. So find the values of P, Q, R and S. So we need to find out these values P, Q, R and S in the state diagram for the given sequential circuit. So we have this sequential circuit, right, which is a JK flip-flop, and we have these outputs and inputs connected to this XOR gate, and this is XNOR gate. This is XOR gate, XNOR gate, and we need to find out the states PQRS of the state diagram, right? So you can break this question into two parts. So how do you break it? The way I approached it, first I will just write down the characteristic table, the excitation table of this thing, and from there I will just find out the states. So first we need to look at this circuit carefully. So here this X is going to XOR gate, and Q complement is also going to XOR gate, and which is finally going to J. So my J will be equal to X XOR with Qn complement, right? And my K is also equal to this X XOR with Qn complement, and my Y, the output Y, is equal to X XOR XNOR with Qn complement, right? So this is Qn complement going to this XNOR gate, and Qn complement to XOR gate. So let's just draw the table first. So here I have X, here I have Y, and then I have Qn, then I have Qn complement, then I have J, then I have K, and then I have Y. So 0 0 0 1 1 0 1 1. So Qn is for 0 0. So sorry, this was Qn. Let's just ignore this column. This was Qn. This was Qn. So 0 0 Qn complement. Let's just write the Qn complement first. 1 0 1 0. J is equal to x XOR with q1 complement. So this thing, so we have to do XOR operation for these two columns. So this 1 0 0 1, and k is also same 1 0 0 1, and y is equal to x XOR with q1 complement, XOR with q1 complement. So that will be complement of this thing 0 1 1 0, right? This is my output, this is my present state, this is my input. So I'll just write it here. So my input, my state, my output, and my next state. So x qn y qn plus 1. So it's 0 0 0 1 1 0 1 1, right? This is my input, this is my state, this is my output, and this is my next state. So x is equal to 0, qn is equal to 0 0 0, my output is equal to 0 0 1, my output is equal to 1 1 0, my output is equal to 1, and 1 1, my output is equal to 0, right? And next state is equal to, so next state we can find it using jk conditions. So x is equal to 0 and qn equal to 0, j is equal to 1, q is equal to 1, so it will toggle, so it will be 1. J is equal to 0, j is equal to 0, k is equal to 0, it will remain as q, it will remain as 1 1 0, j is equal to 0, q is equal to 0, it will remain as equal to q, so it will be 0. And x is equal to 1, q is equal to 1, so it will be 1 1, and j and k will be 1 1, it will toggle, so it will be 0, right? So this is my next state, this was my output. So here let's just check. So I am at 0 and I'm again so now how will we construct it? So here I am at 0 and this is 1. So my present state is 0 and I am going to 1. When I am going to 1, from 0 to 1, when I am going to 0 to 1, when my input is 0, when my input is 0 and my output is 0. Check this thing. I am at 0, I am going to 1 for input 0 and the output is 0, right? 0 0. I am at 1, I am going to 1 for input 1 and for input for input 0, for input 0 and my output is 1. I am at 0, I am going to 0, so I am going to 0 with input 1 and output 1. I am at 1, I am going to 0, so I am going to 0. When I am going from 1 to 0, 1 to 0 with input 1 and output 0, right? So I have constructed the state diagram similar to this. So comparing these two, p is equal to 1 1, q is equal to 0 0, r is equal to 0 1, and s is equal to 1 0. So 1 1 0 0 0 1 1 0. So option D is my right answer. So what is not visible? Which part is not visible? Right side. Is it visible now? Can you check it? Not completely. So let me just check what is not. Right side. Is it visible now? Here I showing me it's visible, but I don't know. Or any of you is facing this same problem? Can someone confirm? So So let me just repeat the question. By the way, any doubts in this question? I'll repeat it, but still any doubts that you want me to focus on? So let me just repeat it. So we have this question. We are given this circuit, and we need to fill up this state diagram. So this is the circuit where my input J and K are equal to x NOR with Q and complement. So this is going to this, and this is going to XOR, and Y is equal to x NOR with Q and complement, right? So based on this, I constructed this table. X, this is Qn, read it as Qn, this is Qn. Let me just this is Qn. So this is 0 0 0 1 1 0 1 1. Then I have written Qn complement 1 0 1 0. So my J and K will be equal to XOR with Q and complement. So 0 1 is 1, 0 0 is 0, 1 0 1 is 0, and 1 0 is 1. So based on this, I have written these two columns, and then Y, it's equal to X NOR with Q and complement. So 0 1 0 0 0 1 1 1 1 1 1 0. So this is my Y. So then I have written here my X, my Qn, my Y, and Qn plus 1. So this is my input, this is my present state, this is my output, and this is my next state. So when X equal to 0, Qn is equal to 0. So 0 0, my output is 0, and Qn plus 1 will be dependent on J and K, 1 1, and it will toggle, that means it will be 1. Then my X equal to 0 and Qn equal to 1, X equal to 0, Qn equal to 1, my output will be 1, and my J and K are 0 0, the state will remain the same, so it will be 1. Then 1 0, my 1 0, that means output will be 1, and for J and K are 0 0, that means Qn plus 1 will be Qn, so that means it's 0. Then I have 1 1 1 1, Y equal to 0, J and K are 1 1, output will toggle, our next state will toggle to Qn complement, so it's 0. So I am getting 1 1 0 0, and Y equal to 0 1 1 0. So here I am at 0, I am at state 0, I am going to state 1. So I am at state 0, I am going to state 1. When I am at state 0, I am going to state 1. When input is 0 and output is 1. Input is 0 and output is 1. I am at state 1. I am going to state 1 only. When input is 0, and my output is 1. I am at state 0. I am going to state 0 only. My input is 1 and my output is 1. 1 1. I am at state 0. I am at state 1 actually. I am at state 1. I am going to state 0 when my input is 1 and output is 0. So my P is equal to 1 1, my Q is equal to 0 0, my R is equal to 0 1, and my S is equal to 1 0, and that is option D. So was that visible and clear this time? Can you just confirm that? Otherwise we can proceed to question number 9. If you are not comfortable with chat box, you can use your mics. Okay, no doubts and visible. Oh, that's fine. So let's just move to question number 9. So question number 9 of today's live session, it states, what's the output signal Q? What's the output signal's frequency for the following circuit with 5 MHz clock signal? So the clock is 5 MHz, and we need to find out the output frequency of the output signal. This is a T flip-flop, and this is a D flip-flop. No, this is T. So this is my this is my clock, and it's a positive edge triggered clock, so this is this. So this is my output. So for positive edge trigger it will toggle. For every positive edge trigger it will toggle. So if this was clock, this is my output. This was having frequency f, this is having frequency f by 2. So my output frequency will be equal to my input frequency divided by 2, and this condition only arises when t is equal to 1. So for t equal to 1 only toggling happens. So for t equal to 1 my output frequency will be my input clock frequency divided by 2. So clock frequency was 5, so 5 divided by 2, so it will be 2.5 megahertz for t equal to 1. So what I am doing here, this is my clock signal, and for every positive edge triggering there will be toggling. So here the toggling will occur, here the toggling will occur, here the toggling will occur. So that means my output frequency will be divided by 2 of the clock frequency. So that means my output frequency will be 2.5 megahertz, and this condition arises only when there is toggling, and their toggling happens for t is equal to 1. So option D is my correct answer. Any doubts in here? So I presume there are no doubts. So kindly confirm after the problem is solved if there are any doubts. I don't want you guys to remain silent if there are any doubts. Otherwise, I'll just assume that there are no doubts. So let's just move forward to question number 10. So the question number 10 asks us, which of the following output sequence Q2, Q1, Q0 is produced by the following circuit. So we need to find the output sequence of the following circuit, and there is one note that is given in parenthesis that all flip-flops are negative edge triggered. So right, all flip-flops are negative edge triggered, and so let me just examine the circuit first. So this is a T flip-flop with inputs as 1, so that means toggling will happen at all the negative edges. This is a clock given to this input, and then Q0 is given to this, and Q1 is given to this. So here Q0 is the clock of Q1, this 1, this is 0, and this is 2, and Q1 is the clock of this, right? So we'll just first start with clock. So I'll just construct the clock. I will mark all the negative edge triggering. So Q2, Q2, Q1, Q0. Let's just assume Q0, Q2 initially were 0, 0. So this is Q0, this is Q1 and Q2. So this is 0, and for negative edge triggering, negative edge trigger, the clock negative edge, the triggering will happen. So here, here, again here. For negative edge, the toggling will happen. So now I'll mark the negative edges of this Q0, because this is the input clock of Q1, of T flip-flop 1. So let's just assume all were 0, 0, 0. So toggling will happen at the negative edges, right? And for Q2, negative edge is here, so only here it will change. So here it was 0 0 0, then it is 1 0, then it's 0 1 0, it's 1 1 0. So if I start with 0 0 0, I'm going to, so remember order, it's q2 q1 q0, these things are pretty important. q2 q1 0, so it's 0 0 0, then I'm going to 0 0 1, then I'm going to 0 1 0, and then I'm finally going to 0 1 1. So the sequence that I'm following: 0 0 0, 0 0 1, 0 1 0, and 0 1 1. So option A is the correct answer. You guys can also check it if initially there were 1 1 1, and you can find out the sequence, but I have done it. So based on these two options, none of the options match, so that's why I started with 0 0 0. So as a home assignment, you can check for 1 1 1. You can see that none of the option matches with this case, so that's why we started with 0 0 0. Any doubts here? Explain if q2 q1 q0 is 1 1. Okay, so here I can show it. I can have a new slide for that. New slide, delete, Control C, Control V, current slide. So q2, let me just draw the clock first. So it is 0. This is q0. If we just start from 1, toggling will happen here. If we start from 1, toggling will happen here, toggling will happen here, and toggling will happen here. Now I'll mark the negative edges of this thing. q1 will be equal to, if we start from 1, it will go down here. If we start from 1 here, it will go up here, and then it will continue. So this is a negative edge, and this is q2. So q2 will be here, and it will remain as 0. So this is 1 1 1, this is 0 0 0, this is 1 0 0, and this is 0 1 0. So q2 q1 q0, it will start with 1 1 1, then it will go to 0 0 0, then it will go to 0 0 1, and then it will go to 0 1 0. So 1 1 1, 0 0 0, then we have 0 1 0 0 1. So none of the option is 0 0 1. That's why I have discarded it. But if it was 1 1 1, we would have this sequence. So is it clear? Okay, now moving forward to question number, this was I guess 10. Now moving forward to question number 11. So the question number 11 asks us, what will be the output frequency of 4 cascaded T flip-flops? Given the input frequency of T flip-flop is 400 Hz. So the question asks us to find out the output frequency given 4 T flip-flops are cascaded. So we know that output frequency, whenever we have this type of circuit, output frequency is equal to input frequency divided by 2 to the power n, where n is the number of flip-flops. So we have 400 divided by 2 to the power n is equal to 4. We have 400 divided by 16, and 400 divided by 16 is simply equal to 25. So input clock frequency was 400 Hertz, so the output frequency will be equal to 25 Hertz. So option B is my correct option. Now I'll like you guys to this question first, and then I'll just show you the solution. It's 410. I think in 5 minutes you will be able to do it. So 4:15 I'll just ask you guys to type in your answers if you're able to do it. Then I'll just show the solution. So which of the state diagram represents the following circuit? So the circuit is given and we have to just mark the correct state diagram. So do it. So have you guys done it? If yes, please type in your answer and then I will show you the solution. Okay, let me just show you the solution. So we have this D flip flop is connected to a 2:1 mux. So if I am at q is equal to 0 and I am at q equal to 1. So when a equal to 0, x0 line will be selected. So a equal to 0, the output y will be going to d and my q will be equal to then 1. So see what will happen. I am at when a equal to 0, this line will be selected and y equal to q bar, then d is equal to q bar, and then q of next state will be equal to q bar. So that means for a equal to 0, toggling will happen, right? And for a equal to 1, y will be equal to q and it will be equal to qn plus 1 will be equal to q only. So this is a equal to 1. That's all. This was what you have to do. So based on the options, so option 4 matches with our solution, so option 4 is the right option. A equal to 0, a equal to 0, a equal to 1, a equal to 1. So for a equal to 0, toggling happens, and for equal to 1, the output remains, next state output remains same as the present state. So were you able to do it? Can just someone confirm at least that part, or was it clear? Should we proceed to question number 13? Okay, let me just assume that this was clear. Please do type in your doubts if you have any. So now question number 13 is asks us, the following synchronous equation circuit is designed with a JK flip-flop and a T flip-flop with JA equal to A plus B bar and K equal to A bar plus B and TB is simply equal to A. If the initial state A and B is equal to 0, 0, then find the sequence of state visited by the circuit. So we need to find the sequence of the states visited by the circuit. So J and K are my inputs for the JK flip-flop, A is the output and TB is the input of my T flip-flop and B is its output. So we know for a J flip-flop is governed by the equation J is equal to Qn plus 1 is equal to, the characteristic equation is equal to JQ complement plus K complement Q. So J, that means here Q is equal to A, so A n plus 1 is equal to J times A complement plus K complement A, right? So this is the characteristic equation of this JK flip-flop, but given is J is equal to A plus B complement, so I'll just write it like this: A plus B complement using the conditions that's given. Then it's AND with A complement plus K complement is A complement plus B whole complement. Then it's AND with A. Someone is in the waiting room, let me just admit the person. So we are doing this thing. So now I'm here, so it's A plus A complement, so it will be A and with A complement is 0, so it will be A complement B complement plus I am having the A complement plus B whole complement, it will be A complement and with B complement, and then we have A, so this will be equal to A complement B complement plus A B complement, taking B complement out, so it will be A plus A complement. We know that A plus A complement is equal to 1, so that means A n plus 1 will be equal to B complement, right? And Bn plus 1 is equal to, we know for a T flip-flop it's TB XOR with Q, and Q here is B, so it's TB XOR with B. So TB here is A, so it's A XOR with B. Now let me draw the table. I have in present states A and B. These are my present state, and then I have the next states A plus and B plus. So it's 0 0 0 1 1 0 1 1. So A plus is equal to B complement, so it will be 1 0 1 0, and B plus is equal to A XOR with B, right? So A XOR with B will be 0 1 1 0. Now we have to follow the sequence that it will, we have to find out the sequence it will follow. So it starts with 0 0, it's given initial state was 0 0, and it goes to, with 0 0 it goes to 1 0. Now I have my present state as 1 0, so I have to check this. So with 1 0 as my present state, it will go to 1 1. Now with 1 1 as my present state, it will go to 0 0. So the sequence it will follow 0 0 1 0 1 1 0 0. So that is option B. So option B was the correct answer to this question. That was question number 13. So if you guys have any doubts, please type in. So I assume there were no doubts. So let me just go forward to question number 14. So the question number 14 asks us, what is the output and the state of the circuit represented using below state diagram for input sequence 111. Initially the circuit is at state A. So we need to find the state and the output of the following state diagram, and given that the we are at state 0A and we have the sequence 111. So I am at state A and my input sequence is 111. So when I am state A and my input is 1, I'll go to B based on the state diagram, and my output will be 0, right? Now when I am at B, I'm getting an input 1 again, so I'm getting an input 1 again. I'm going to C with output as 0. Now this one is done, this one is done. Now the third one at C, when I'm getting 1 as input, I am remaining at C only, and my output will be 0. So after the sequence of 111, when I started with A, I am ending up at C, and my output is 0 and my state is C. So output is 0 and state is C. So option C is the correct answer to this question. So any doubts for this question? This was a pretty simple question. I assume there are no doubts, but still if there are any doubts, please type in. If not, let me just read out question 15. So this is again the question that I would like you guys to do first, then I'll just show you the solution. So it's 4:23, it will just take 3 minutes. So at 4:26 I'm expecting your solutions and answers. So after 3 minutes I'll just show the solution. So let me just read the question first. Consider the following sequential circuit to determine the state sequences of Q0 Q1 for next 4 clock cycles if the initial state is given as 1 1. So the initial state is given as 1 1, and you need to find out the states for the next 4 clock cycles. So it will be done in a couple of minutes. So after that I'll just show you the solution. You guys first do it. So please do it. So have you guys done it? If someone has done it, please type in your answer, otherwise I'll just show the solution. Okay, let me just show you the solution. So here we have two T flip-flops. So the clock is going to this T flip-flop 0, and the output Q is going to as clock for T flip-flop 1. So if you carefully examine the circuit, so this is a positive edge triggered flip-flops. So here I'll just draw the input waveforms for the clock first. Let me just draw the clock first. And I'll just label the positive edges. Here I'll just write down Q0, and here I'll have Q1. So my input state is, initial state is 1 1. So at 1 toggling will happen, and again here toggling will happen, here toggling will happen, and here toggling will happen. So now I'll just label the positive edges here, and here. So this will go to here, and this will go here. So initially it was 1 1, then it's 0 1, then it's 1 0, and then it's 0 0. So if I start from 1 1, I go to 1 0. So here see, as I told you earlier, that time we had Q2 Q1 Q0. Here I have Q0 Q1. So you need to be careful with these things. So the order that question is asking is Q0 Q1. So it's Q0 Q1, so it is 1 1, then it goes to 0 1, then it goes to 1 0, then it goes to 0 0, and then it goes to 1 1. So it's 0 1 0 1 1 0 0 0 1 1. So option A is my right answer. So option A is the correct answer. Any doubts? If not, let's just proceed towards question number 17. Question number 16. Question number 16. Yeah. Question number 16. The following state diagram represents which of our input equation? Given dA is A x y, where dA denotes D flip flop with output A, the x and y are inputs to the circuit. So we need to find out the state we need to find out the expression that represents the state diagram. So what we'll do, we'll just first write down the inputs A, X, Y, and we'll construct the characteristic table out of it. So we have A plus, so by A plus I mean the next state, so it's 0 0 0 0 0 1 0 1 0 0 1 1 0 1 0 1 0 0 1 1 1 1 1. So by taking the help of the state diagram, we can construct this table. So this is my present state and this is my inputs. So just for the sake of clarity, I'll just write here. So my inputs are 0 0 and my present state is 0. my inputs are 0 0 and my present state is 0. Where am I going? I am again going to 0. My present state is 0 and my inputs are 0 1. My present state is 0, my inputs are 0 1. Where I am going? I am going to 1. My present state is 0, my inputs are 1 0. Where I am going? I am again going to 1. My present state is 0 and my inputs are 1 1. Where I am going? I am going to 1 again. Right? Now I am at here. Now my present state is 1 and my input is 0 0. Where am I going? I am again going to 1. Now my present state is 1 and my input is 0 1. I am again going to 1. My present state is 1 and my input is 1 0. I am making a transition to 0. And my present state is 1 and my input combination is 1 1. I am again staying at 1. So this is my characteristic table. Now I can write down the equation that describes this state diagram. So I have a, x and y. This is 0 1. So this is 0 1 1 1 and this is 1 1 and this is 1, right? 1 1 0 0 0 0 1 1 1 1 0. Yeah. So what we can do is we can construct a chord and we can have two pairs. So what we have finally is dA will be equal to this will be equal to the chord. So the chord term coming out from the chord, that is a changing, that is y. Then the pair terms, so this is a and this is x complement plus this is a complement, then x. So we have dA is equal to a XOR with x plus y. So dA is equal to a XOR with x plus y. So option 3 is the correct answer. Now moving forward to question number 17. So the question number 17 asks us, which of the following statements are false? So again read this thing, which of the following statements are false? So we need to identify those statements which are false. The number one statement is characteristic equation of a flip-flop is a minimized representation of the next state by considering present states only. A don't care in excitation indicates that a specific transition will take place irrespective of the variable under consideration being 0 or 1. That's correct. Number 3, characteristic table shown in tabular form from what as input is required to move a flip-flop from one particular state to other. Correct. And the 4 is the state analysis table lists all the inputs of flip-flop at a given state and finds out next state using flip-flop truth table and also notes the final output. Number 5, state analysis result in presented through a state transition diagram and or a text description. So based on these statements, the statement that is incorrect is number 1, characteristic equation of a flip-flop is a minimized representation of next state by considering present input only. What it should be characteristic equation of a flip-flop is a minimized representation of a next state by considering present state input and present state. So present input and present state. So this is incorrect. And also the third statement is incorrect. The third statement states the characteristics table shows in tabular form what an input is required to move from flip-flop from one particular state to another state. In reality, it's the excitation table that shows us that what input is required to move from one state to other state. So 1 and 3 are incorrect and other rest of them are correct. So 1 and 3, so option C is the answer to this question. So any doubts? Okay, now towards question number 18. The state diagram of sequence detector is shown below. Show state S0 is the initial state of the sequence detector. If the output is 1, then so what this question asks us? This question asks us to find the sequence. Basically, it's the sequence detector, and we need to find out the sequence detector. We need to find out the sequence that is detected. So if the output is 1, when question states if the output is 1, that means the sequence has been detected. So we need to find out the sequence. So how will we find out the sequence? We'll just simply look at the forward propagating arrows and we'll just follow them. So I'm at S0, and my forward propagating arrow is 0, and I'm going to S1, right? Now I'm at S1 and my forward propagating arrow is S2, towards S2 with input as 1. So I am at S2. Now I am at S2 and I am going to S3 with input 0. Now I'm at S3 with input 1. I am moving forward. With input 0 I am going back. That doesn't help me because I am finding the sequence. I am only looking at forward propagating arrows. Now I am at S3. I am going towards S4 with input as 1. And now I am at S4. I am going to S3 with input 0 and output 1. So here output 1 is detected. So the input sequence that it followed to get the output as 1 is 0 1 0 1 0. So this was the input sequence that needed to be detected. And what was my output at these locations? So when I was at 0 and I with input 0, output was 0, then my output was 0 again, then output was 0 again, then output was 0 again, and once this 0 came at S4, my input sequence got detected and my output changed to 1. So this was the input sequence that needed to be detected. 0 1 0 1 0. So that was all for today's lecture. I think we have some time, so if you have any doubts regarding this question or any other question that we solved previously, please ask. Okay, I can repeat question number 18. So question number 18 asks us, the state diagram of a sequence detector is shown below. State S0 is the initial state of sequence detector. If the output is 1, then so basically if the output is 1 means the sequence has been detected, and we need to look at the arrows and find out the condition, find out the input condition for which the output becomes 1. I am at S0 and I am moving forward to S1 with input 0. Then I am at S1 and I am going to S2 with input as 1. Then I am at S2, I am going towards S3 with input as 0. Then I am at S3 and I am going to S4 with input as 1. Now I am at S4 and I am detecting my sequence by going towards S3 with input 0 and output 1. So that means for input sequence 0 1 0 1 0, my sequence has been detected. And if you carefully examine the outputs goes from 0 0 0 0, and once it hits this 0, the output changes to 1 and my sequence has been detected. So any other question you would like me to repeat? Since we have 5 minutes, I think we have 5 minutes, we can discuss some question if there are any doubts regarding any question. So question 12, what was question 12? Let me just check. Okay, yeah. So question 12, okay, so we have this question, which of the state diagram represents the following circuit? So we have this circuit and we need to find its corresponding state diagram. So we have a D flip-flop and which is connected to a 2:1 mux. So let's carefully examine this mux first. So when A is equal to 0, it will select this thing. So output will be Q complement, right? And this Q complement will be input to this D flip-flop. And when D is equal to Q complement, that means my output is equal to Q complement. So the toggling will happen. And when A is equal to 1, so that means A is equal to 1. So you can simply see A is equal to 1, D is equal to Q. A is equal to 0, D is equal to Q complement. So that's what I have written here. So when I am at Q equal to 0, so when A is equal to 0, toggling, so this is Q is equal to 0 and Q is equal to 1. When A is equal to 0, D will be Q complement and Q plus will be Q complement. So toggling will happen right here. So for which case, when A is equal to 0. When A is equal to 0, my D becomes Q complement and then next it will be Q complement. And for A equal to 1, it will just remain at the same state. So is it clear? So any other doubts? We have some 5 to 6 minutes. We can discuss some questions within this time. If any doubts regarding any question? Okay, I think you are having some connection trouble, so you can refer to the recording that will be uploaded on the YouTube channel. You can have a look at there. So for others, are there any doubts? If there are no doubts, we can close this today's session, and we will meet next Sunday, that is 26th March, Sunday from 3 p.m. to 5 p.m. There we will be discussing the problems related to week 8 lectures. Okay, thank you guys for joining in. See you next Sunday. Thank you.